Most important comment is that this is a joint work with Tawhid Zaman from MIT and Shankar Bhamati at the University of North Carolina. And they're genuine members of the Twitter generation. It inevitably comes a question whether I'm actually a user of Twitter, and I confess that I'm not. But this is not a great surprise. I don't even have a TV. So this is technology as I'm a slow adopter. I'll tell you a bit about Twitter in case you haven't been using Twitter yourself. Of course, I suppose half of you are subscribed to the real Donald Trump tweet. Actually, what I'm engaged with in this data is what's called retweets. So if you subscribe to the Twitter feeds of an individual and other individuals subscribe to your Twitter feeds, then if you receive a tweet, you have the opportunity to retweet that tweet with a comment. For instance, Trump could say something, and then you could retweet it to your friends, and you could say how stupid that is. So that would be an example of a retweet. Now, retweets are a measure of the social importance of the person who is being retweeted. And so this feeds back into the notion of social importance. So here's a...
Mike,
yes?
Could you please set up what the whole thing is? I have no idea where... Yeah.
Okay.
You say subscribe. I have no idea what's going on.
Oh, okay. So there exists some individual or organization. For instance, for instance, the American Math Society probably has a tweet. So you can go to the computer, subscribe to their Twitter feeds, and then...
Which is what, like an email message?
It's like an email message. It's a very brief, it's 140 character quick message that says, our main talk is beginning now. And then you would get that feed, and then you would know that you should go to the main talk. And if you wanted to retweet that, and you were a broadcaster on Twitter, then you could retweet that, and then you could say, "Oh goody, it starts," and that would be a retweet. Okay, so that's Twitter and retweets. So here's a data that's not perfectly captured here, but this is an example of the type of data which we got, which was a window of data, typically 3 to 4 hours, having to do with a social event, either a soccer game or in this case it was an awards banquet of the Black Entertainment Network, BET Television Awards, where Lady Gaga happened to be receiving a prize at this particular event. And
can you describe Lady Gaga to
Yes. No, my cultural knowledge ends with the Plantagenets and Stewards, I think. So we studied 13 different public events, and so here is one involving a football match. Here's the BET Awards. Here's a World Cup Awards, and there's a tennis match. And these are tweets, and what we've got here for the arrows are the retweets. Okay. Sporting events, news events, range 4 to 6 hours. Empirically, the graphs are very tree-like. So in these, it's a bit hard to see them, but we've drawn all of, yes, Samantha?
So what are the nodes here? Are these individuals or tweets or?
The nodes are individuals who
Send these tweets to each other, yes.
And the edge, I draw an edge from B to A if B retweets a tweet received from A. Okay. Measures the importance of A. Empirically, they're very tree-like. There are almost no cycles, and they're just a large component. So what we actually model is the giant component of this graph, and we arbitrarily delete edges that would break cycles. So we give ourselves a tree, but that requires really quite a minor surgery. So they have one giant component, that's what we model, and the graphs are taken as undirected, so the degrees tell the whole story. Now here is you ask about Lady Gaga, that's a picture, not a rather imperfect one of Lady Gaga, whoever she is. This is another picture of another truly famous person, Justin Bieber, who I don't know who he is. This is Kim Kardashian, and I certainly don't know who she is. Oh, and Drake, who I profoundly do not know who he is. So here we have a superstar, and the phenomena is, which is rather different than other forms of social network graphs, is that the superstar has a degree that grows linearly, approximately linearly. So that's the phenomenon that we wish to capture in a model, and we do this in the simplest conceivable way. So just a few more empirical facts, stylized facts, if we're doing financial economics. You find that the max degree is growing proportional in n, and now that's different than you would find for the max degree in a preferential attachment graph, where the max degree would grow like the square root of n. And certainly it would predict sublinear max degree. So here's how we're going to construct the model, or what the nature of the model. We're going to have it completely, which is going to be a one-parameter model. We can introduce further parameters, and we've done that in the paper. But the one-parameter model is the most stripped-down model you could conceivably imagine, and it's just the p, which is the frequency corresponding to the growth rate of the maximum degree of the superstar. Okay. So the superstar, first person shows up, the first edge has to be attached to the superstar. We call the superstar V0. A new vertex comes along, and it's either attached to the superstar with probability p, baking into the cake the linear growth of the degree of the superstar, or, according to preferential attachment, it's attached to one of the non-superstars. So attach with probability p to the superstar, else with probability 1 minus p to a non-superstar, and non-superstar attachment rule, probability proportional to its degree. That's the preferential attachment rule. Of course, there's many variations on preferential attachment, and you can incorporate those variations here, but I'm going to stick with the most stripped down version in this discussion. So there's a bit of a picture of how that evolves. Only model parameter is p. But that has some interesting benefits. P is trivial to estimate, and that then gives you a prediction about the degrees of all of the other vertices. So this is a highly testable model. Now it's not something that you can be very confused about how to test. So there's our baked into the cake is that we have that the degree of V0 is p, but that's all that's baked into the cake. And so p, the feature which we can easily measure from the graph, predicts all of the other features that we would hope for or expect in the graph. So our model's quite testable. And now here's kind of the non-trivial fact. Consider the maximum degree of the non-superstars. Then there exists a parameter gamma, such that once you normalize by gamma, you get convergence to, it's not convergence to a constant, but it's convergent to a non-trivial positive random variable, as one expects commonly in theory of martingale convergences. And we have this interesting parameter here, this little guy here. I don't use this little, the only time I use this little thing for is to play with my cat. So, but once in a while it's useful. So, that fact. What else have we got? So we get up to this prediction for all of the others. Now let's look at the model. So now let's consider the empirical degree. We'll use the cat button. We'll use the realized degree in the random superstar graph. So this counts the number of vertices that have degree k. So it's the empirical frequency of the degree k vertices. And this ends up giving us a probability mass function, a density on all of those remaining k's. Now this looks like it might not be pleasant because here we've got a k, there we've got a k factorial. You wonder how these add up to 1. Well, this is in essence a k factorial, so it's bringing it down there in a proper way. And the theorem, of course, is that we have convergence of the empirical frequencies with probability 1. Now, this is kind of a funny thing. This is an empirical probability mass function. This is a probability mass function. But we have almost sure convergence of the corresponding probability mass functions. And the key point is that this object actually scales like k to the minus beta, where beta is b. In the plain vanilla preferential attachment model, we would have 3. So this actually goes down more rapidly than you would have in the preferential attachment model. And as p, the degree, the rate of growth of the popularity of the superstar increases, you would even get more rapid decay. So it's not like you've just got allocation of the superstar, then the result is subsequently plain vanilla preferential attachment. Somehow the absorption of the superstar causes more rapid decay among the non-superstars than would otherwise be expected or predicted. So that's the nature of that contrast, and we get a faster than preferential attachment. Okay. So let's put these in perspective. We've got the features of the model, the superstar degree, maximal non-superstar degree, and the distribution. And in the superstar model, of course, baked in the cake is p times n, and that doesn't exist in the preferential attachment model. Preferential attachment has no superstar, which kind of makes this interesting. And the retreat graphs, we looked at a bunch of them. We looked at more than the 14 that we reported in the paper. And this superstar phenomenon is really there. So there's something worth attending to in that data. For the superstar model, we have a degree exponent for the non-superstars, and that's in the simplest preferential attachment model, you would just get a half there. So here our p, which was brought in by the first feature, empirically easily observed, forces us to this second level. Now, when we look at more elaborate, rather than just the very simplest preferential attachment model, you get more elaborate formulas, but this already tells you much of the story. Degree distribution law, and of course corresponding 3. So that's kind of the full contrast of these in a nutshell. So how well does it do? And we use the actual data of 14 events to try to compare our observed, so the hats. By the way, on Wikipedia I sometimes use the name hat check because when I edit things I tend to put in little hats on all the estimators that everybody seems to have left out. I hate it when an estimator doesn't have a hat on it. So we'll consider the observed degree distributions for the empirical graphs, and we'll want to compare that to the theoretical asymptotic distribution under the superstar model. And now we don't have anything that's truly analogous to a chi-squared goodness of measure, so I can't report any p-values. That would be an interesting thing to do, but everything's so massively dependent and kind of confusing, there's not much direct hope of that. There might be computational approaches. But we would certainly expect that the empirical degree frequencies will be behaving like our asymptotic degree frequencies, where we've used the plug-in estimator. We've plugged in the p hat for the p in the theoretical model. That's a common process. And the basis for test, preferential attachment, would always make this prediction. So here's a kind of a plot for different events. This is events involving a circumstance around a basketball player, a Brazil-Portugal football event, Black Entertainment Awards, and a tennis event. And here we have, with the dots, there's the theoretical. Here's the plug-in, and there's preferential attachment. And you know, it's a little bit off. There's a trick in statistics, widely known, that if you want to make your data look bad, you plot the residuals. But if you want to make your data look good, you plot the observed versus the expected. And I've chosen the second path. So when we plot the observed versus the expected, it looks good. Well, this is kind of kludgy here, but you can anticipate that that's because of the integralities of degree ones and corresponding here. So we don't really have official tools, but I found these plots to be encouraging. Now, relative error, a little bit scarier thing to have to contemplate. Relative errors are often disastrous. If you ever do a financial time series, I encourage you to never do this. It will depress you beyond imagination. But here it works out relatively better. So the horizontal axis are our events. So we've got 13 events in these cases. And this is the relative error as we described on the previous foil. There's the relative error for the preferential attachments. Those are all pretty brutal, but you would expect that for degree 1. That's kind of the sloppiest degree. And by degree 2, the FP hat plot, oops, now I used to go back. The FP hat plot is there's a little bit more of an honest competition here. And so this gives you an idea of how they go. Each to his own, but I find this is vaguely argues in favor of the superstar model. Okay, so a cool thing is the superstar model gives you a mathematical link between the superstar degree and the degree of the non-superstars. Now, if I looked at a preferential attachment model which was other than the completely plain vanilla preferential attachment model, I could make some of these pictures look quite a bit better. So you can make the other degree sequences come more closely into line. Now we looked at real events. Our first property is baked into the cake. Now, how does one analyze the superstar model? It turns out you'd think that it's something that was as simply described as it was would be very easy to analyze, but it actually ended up being somewhat tricky to analyze. And the proto idea is to use branching processes. They always have a role anytime you have a tree that's growing. Here, multi-type branching processes turned out to be useful, and that's actually kind of a specialized topic that I didn't know much about, but I managed to learn some during the course of this project. Yield processes don't come with a superstar, so you have to build one, and we're going to build one by first creating a plain vanilla multi-type branching process. And it's a reasonably dense argument, but I can give you the picture. And here's the news you can use. You get a benefit from using multi-type branching processes because if you have types in a multi-type branching process, then you can do surgeries on that to create other types of graphs. Now that's a rich recipe. There are lots and lots of things you can do that way. So in our particular case, we start with two types red and blue. So there's a typical multi-type branching process. I'm beginning with a V0, no superstar in this model. This is going to be just the non-superstars. And how am I going to evolve this? Each vertex is going to give birth according to a non-homogeneous Poisson process that has a rate that's equal to 1 plus the number of blue children. So this vertex would give birth at rate V2, this vertex would give birth at rate 1, so this would give birth at rate 2, this would give birth at rate 2. I let that parameter be the number of blue children at time V. At time T units after the birth of the vertex V. Each vertex is painted red with probability P, or painted blue with probability 1 minus P. Here you can anticipate that eventually I'm going to convert these red vertices into the acolytes that are directly attached to the preferential attachment model. Of course, interesting time for us is the T is in real time, so we're interested in the stochastic times when we have 10 n guys in the process. That's an example of the evolution. So here's how it would go. Once we've, say, grown a multi-type branching process of size 6, then I add the superstar exogenously, and then I'm going to take all of the edges from the red vertices and I'm going to connect them to the superstar. That's my surgery. So I'll go back and do that for a second. So you began with just the multi-type branching process. You add the superstar exogenously. You connect all of the edges, which were edges between the red guys, and you send them on up to the superstar. So now, because the percentage of reds in the whole graph was equal to P, you've got the degree P, n times P for the superstar is anticipated. And then, when the surgery's done, all the connections are made, all the colors are erased. And now that's your superstar graph. Now, at the end of the day, of course, you have to prove, I had two descriptions of the superstar model. One was you just attach directly and then you use preferential attachment. Description 2 was this model using multi-type branching processes. First thing you have to do is prove that these two are equivalent. That's not a difficult thing to do. And then once you get the machinery of the multi-type branching processes, and you know there's a substantial literature on multi-type branching processes, then you have to leverage that literature and the associated martingales in order to prove the rest of the theory that you're interested in. So I will send us on to our cake by just reviewing this piece. You have to calculate some joint, you have to compute some conditional distributions, but again, these are reasonably straightforward. Now, this is posted on the web so you can find it. Martingale arguments come in through the existence of limits to non-trivial random variables, more conditional probabilities. Now, here's my punchline in the last 1 minute. Yep. How long ago? Well, we'll leave time for questions. Okay. One mistake that I've made in my long career is I've often failed to do simple things that I should have done. And there are lots of examples of things. They're just you take a stylistic fact, something that's true in the world, and then you make the change to your most off-the-shelf model that accommodates that stylized fact of the real world. So if you'd have done that, say with the AR1 model, and having acknowledged that there really is volatility that changes over time in financial time series, you could have assigned this to the class, said, class, tomorrow observe that we have volatility that it changes over time. So tomorrow, come back with a variation on AR1 and we'll discuss them. Half the class would have invented Arch and half the class would have invented Garch. And then you have this puzzle about which half of the class to give the Nobel Prize to. So I've learned too late not to be embarrassed by simple modifications. Of course, another very nice one is the Neyman-Scott model. If you go out and you look at a bunch of plants, then plants are not placed on the planet according to the Poisson process. They're placed in according to of little groups. If you wanted to think of the simplest way to create little groups, you'd lay down a Poisson process. Then you'd take a sample by some rule, according to some, say, distribution, spherical normal, around the points in your Poisson process. This is the simplest modification of the Poisson process that gives you spatial clumps. Turns out to be very widely studied, very beautiful, very interesting, very rich in lots of ways. And that's the same is true for the GART. So note to self, don't be afraid of simple modifications. Nature of the difficulty here was there was some technical work to be done. And it's kind of interesting that you do recapture preferential attachment as p goes to 0. So you can think of this as a perturbation of preferential attachment. It's always not so much for our community, but there are other communities toward where the whole point of life is to find out that some model is a perturbation of some other model. Using this, it looks like preferential attachment with a twist, but the differences are, I say, huge there. Now you'd spell that Y-U-G-E now. That's, but it's huge. It's easy to use, it's easy to reject. Let me back up for a second. Plain vanilla superstar model is rigid. If it works, great. If it doesn't, you'll find out quickly. Has the charm of a one parameter model where the parameter itself is trivial to estimate, and there are lots of ways to tweak it if you have an important and appropriate purpose for tweaking it. Let me emphasize that I certainly wouldn't have engaged this if it hadn't been for Tauhid Zaman and Shankar Bhamadi, who were very, very energetic, insightful collaborators on this project. Thank you very much.
Right, thank you very much. Any questions for Mike?
Savanta? Oh.
Well, okay.
Oh, sorry.
So you just argued that it was good to have a very simple model, but also you mentioned that one could put in more parameters. So I mean, one obvious thing, which I guess you thought of, is that here you have one superstar, and that depresses the distribution, degree distribution of the others. You get a slower exponent for fast tail zone. So, but maybe Justin Bieber also is some kind of half superstar. So have you thought of putting in some kind of more than one superstar, some semi-super?
No, that actually is one. That is an interesting variation that we did not consider. We considered the kind of plug-in alternatives where we then took, say, elaborations on the preferential attachment model, say with an additional parameter alpha where parameters would be degree plus alpha, etc. And that was natural and rather automatic. But we did not consider multiple superstars or twin superstars. I mean, two competitive superstars. That would be interesting. I think that in that case you might lose some of your natural tree structure.
So when thinking about modeling a process like retweeting, it seems natural to think about the network that's happening on, since a lot of people are being exposed to these tweets that they could retweet via the following network. So you chose not to use that information at all. Is that partially to sort of make it so that you can do this modeling without having that data? I mean, some of the other models of retweeting processes or these propagation processes usually use the underlying sort of substrate, even if it's possible for people to sometimes jump straight to the superstar and interact with their content and get infected from them. People are usually doing the process on the following graph.
We did not think about using additional data. We were trying to strip things down to get something that was as simple and graph-like as possible, mainly because that was just part of our homegrown technology. Other things that we thought about using but didn't always have at that time, and they're dynamic, was the number of subscribers to a particular issuer of tweets. That would certainly give you a lot of insight into the likelihood of subsequent retweets. But I didn't think about using more complicated things, but one certainly could.
Final question?
Yeah, there's some more data that you could have used, I imagine, which is the timestamps that go with the retweet.
Yes.
I suspect that the dynamics of your model don't really agree with the timestamps of the actual retweets. Is this a concern, or should we not worry about that?
Well, we took all of the retweets that were within a given time window, but we didn't look at the timestamps within that window. Sometimes it'd be interesting to do so, and I don't know anything about the dynamics if one did. Here the sense is that some people are fast retweeters with just an additional comment. Sometimes a person is going to try to compose some joke or talk to his friends before they decide to retweet. So it would be rich and interesting to incorporate that data, but we didn't.
Okay, let's thank Mike
Right.
and the other speakers.